Today, we have with us Dr. Mia Siochi. She's currently a materials engineer with the Advanced Materials and Processing branch. She has specialized over the last 20 years in researching and developing nanomaterials for application in structural nanotube composites and nanotube-based multifunctional components. I know this is a very interesting subject. We read a lot about it and have been reading about nanomaterials. So her talk today is going to cover the a little bit of the history of how nanomaterials were developed over this time and how they are becoming more available now. And that's always been the limitation of nanotubes, is you can't produce enough of them. So I'm very interested in hearing what she has to say. And I would invite you all to welcome Mia this afternoon. If you have any questions, send a personal chat to me. And then after the end of the talk, I will go through the list of questions in order. Welcome, Mia.
All right. Thank you, Dan. Good afternoon, everyone. Thank you for the invitation to talk to you all. I thought when Dan invited me, I thought, it would be interesting to talk about how NASA was involved in advancing the maturation of carbon nanotubes. We've been working on carbon nanotubes since around 2000. And the specific focus of our work is on the structural properties of carbon nanotubes. So I thought, I've been looking back at how things have evolved and thought I would share that perspective with you all. Okay, so what are carbon nanotubes to begin with? If you imagine carbon atoms lined up in hexagons like in a sheet of chicken wire, it looks like chicken wire. And when you fold it up and fold it, and it forms cylinders where the diameter is on the order of nanometers. And so these materials are on the scale of 1/80,000th the diameter of human hair. At that scale, when you look at its properties, and here I'm showing a plot of specific modulus and specific strength, those properties are way up here. Typically people say it's 100 times stronger than steel. So, in the context of materials that are used for aerospace structures, what does that look like? This plot is an excerpt from an SATM that Charlie Harris published back in 2002. And so, you'll recognize aluminum, which is ubiquitous in aerospace vehicles. And now we also have composites, carbon fiber reinforced composites. And so because composites are stronger and lighter than aluminum, right, we're moving towards that as the state-of-the-art material for things like aircraft, like the 787 is 50% composites. And so when you look at, the best material we had available back in the early 2000s, and then look at the nanoscale properties of carbon nanotubes, anywhere in this space, if we can get, carbon nanotubes into structures, it would save us a lot of mass in structures. So why do we care about that? Because especially for space exploration, the amount of propellant that's needed to escape Earth's gravity gets, you need more and more of it as you travel farther and farther. We often hear about the cost of launching, the cost of launches to be about $10,000 a pound. That's true if we're going to low Earth orbit. But now as we think about going to the moon and eventually also going to Mars, those costs go up by orders of magnitude just based on the rocket equation in this case. And so if we can reduce structural mass, it will either help us reduce the cost of launch, or at the constant amount of payload, it increases the amount of payload that we can launch if the dry weight is is lower. And so this is again out of Charlie's TM. What was the motivation for looking at basic research for carbon nanotubes back in 2000s? And the systems analysis that was done then was based on a reusable launch vehicle model. And this plot is just a normalized vehicle dry weight, right? And so if the reference material has a mass of 1, carbon fiber composites were projected to reduce mass by 55%. And considering the nanoscale properties of carbon nanotubes, their projection at that time was 82% reduction in mass. Now, obviously, this is very crude, but at that time, this is based on information that was available then, and suggested that it's important for us to be looking at carbon nanotubes and see how we can use it. So with that background, and looking back at how the technology maturation has evolved, I think about how NASA's role has evolved in terms of three things: technology push, a technology pull, and how we do things now with technology pull, guided technology push. And I'm going to talk a little bit about each one of these. So for technology push, what do I mean? Usually these are for technologies that are new and different, pretty mature, and in the case of carbon nanotubes, very highly hyped, and I'll show what I mean by that. And you hear the words like game-changing or revolutionary, right, for technologies that can potentially be disruptive. And when you have technologies like that, it spurs significant investments in basic research. And in fact, the US government did invest a lot in nanomaterials in general, carbon nanotubes being one of those. And as with a lot of new technologies, the cycle of maturation goes through what's called the Gartner hype cycle, where you're plotting expectations versus time in general. And so in this case, in new technology cases, there's an innovation trigger, which triggers a lot of interest in this technology. And when there's a lot of interest, then you have a lot of investment. And because of the significant amount of investments, then there are inflated expectations of what these materials can do. And in the case of carbon nanotubes specifically, there are so many interesting properties, not just mechanical properties, but also electrical properties and thermal conductivity of these materials that people are dreaming essentially of what are the different applications, what problems can it solve. And generally speaking, when you have inflated expectations like that, it's very rare for technologies to meet that expectation. So then investments drop, and you have what's called a trough of disillusionment. And then in this trough, you have fewer people, entities who are working on the technology seriously to get it up the slope of enlightenment and eventually into use. So what does that look like for carbon nanotubes? Indeed, this is part of federal investments in the National Nanotechnology Initiative, which President Clinton announced in 2000. And what that has resulted in is massive, massive investments to the tune of, over the last 20 years, on the order of $27 billion. Now, it's not entirely on carbon nanotubes, but nanotubes were part of the technologies that were covered by that initiative. And for nanotubes specifically, what that resulted in was a lot of publications. So I'm overlaying here in green the number of publications over the years. The innovation trigger was a paper in 1991 by a Japanese researcher in NEC, where the novelty of carbon nanotubes were recognized. And so, there was some interest. You could see some publications there, but very clearly, once the US invested in nanotechnology, then you had this surge of publications over about 10 years. Of course, there's a lag in publications versus when funding started, and you see that here. And so what this curve shows is actually the total. I looked it up. This is numbers from about late 2019. That's on the order of more than 200,000 publications on carbon nanotubes alone. And so you have, a massive amount of information coming, right? Because people were studying this what they hope was a magic material, honestly, And so, in the context of publications for materials, if I compare that to carbon fiber composites, carbon fiber was discovered around late 1950s, like 1958, and it started being used in the 60s. And between the 60s and around 2019, when I looked up number of papers for carbon fiber, it was maybe about a third of the number of publications of carbon nanotubes, for a shorter span of time. So that, I think, gives you a sense of the interest in this material. And it's not just in the US, by the way, so there's global interest in this material, right? But you notice also, most of those papers were published, around, the work was done around this time, before 2010. And at that time, the material that they were looking at, this is what the carbon nanotubes look like. Initially, they look like soot. They look like powder, right? But very expensive powder. When we started looking at this material, NASA's investment started around 2000. We were getting this material in the order of $150 per gram, and the quality wasn't consistent. And so a lot of this work was done on this type of material. There was I would say, a critical paper around 2010 on carbon nanotubes specifically for structural properties, and properties that gave us a sense of its potential for applications that we were envisioning. And that material was based on what's shown here. The material evolved from being a powder to being able to be produced in sheets. So these sheets are about 8 feet by 4 feet. And that production was possible because of a company named Nanocomp. They are in New Hampshire. And they're the first to make large-scale material like this. This material started being available in 2004 because of DoD investments in Nanocomp. And so if you notice, the paper was published in 2010. If you match it up with the Gartner hype cycle behind, this was already at the downturn of funding available for nanomaterials and carbon nanotubes specifically. Interest waned because, it just did not live up to the hype. Right. So, what is that? Why is that? Because realistically, when we evaluate whether or not this material is useful for what we envisioned it to be for aerospace, I'm bringing back the plot of specific modulus and specific strength. Most of the papers that were published then were from matrices that were lightly doped with carbon nanotubes. And so, on their own, if you did not plot the properties of these lightly doped composites on this plot, what it showed was relative to the matrix. I mean, these composites are basically made with polymer that were doped with this powder at very small quantities. And in very small quantities, you have significant quote unquote increases in the properties of the resin itself, of the polymer matrix. But you also get huge orders of magnitude increases in electrical conductivity. So, there was, of course, excitement, including us. We had internal work on this, and we were focusing on, how does it improve the starting material? But if you put it in terms of, actually feeding it into the use, and your competitions up here, it clearly is inferior, right? So what were the lessons learned from that time, which is, I would say, about 5 to 8 years of investments, maybe between 2000 to 2008. What we learned was these materials were very analogous to short chop fiber composites. At that time, material supply was limited, and also the quality was not consistent. And because we're mixing powder with effectively what is like glue, you can get very low volume fraction. doping, because when you try to put more than 5% of these nanotubes into the matrix, the viscosity of the whole slurry will go up and it's very hard to process. And realistically, there is limited improvement in the mechanical properties of the matrix. However, the payoffs are noted in electrical properties. So instead of people just focusing on mechanical properties, you then start hearing about multifunctionality, meaning, oh, now we can have a material that not only can be a structural material, but you can also have electrical conductivity, have thermal conductivity. And so there's a whole slew of papers on multifunctional materials. So, when we look back for the work that our team did within NASA, and specifically within Langley, which is, I think, where the core of the work on structural CNTs happened. We had a lot of papers and presentations and patents, and in fact, some of our papers are really highly cited to this day. I think there's one paper we had on how to disperse carbon nanotubes. It's probably got over 900 citations, which is not usual for us. So despite the attention and despite what we can claim as accomplishments at that time, if we're being honest, the structural applications that we envisioned did not materialize. Okay, so let's take a look at what happens with the technology pull. In that case, the performance needs are identified, but they're identified because a mission has been identified and the requirements are set. And therefore, what we're talking about is there's a schedule that we have to fit into, and so. And when you have very specific requirements and there's a schedule for mission success, typically people are very risk averse. So you don't usually think of what we call an emerging material technology being a candidate for that kind of use. However, that's what happened with carbon nanotubes on the Juno spacecraft. Juno is launched in 2011. This is actually built by Lockheed Martin, and I know the person who actually worked on this and inserting nanotubes into Juno. It was not for structural properties, but it was based on our learning, the knowledge that we gained by working with carbon nanotubes on what value this material can bring. And so carbon nanotube composites were actually used on the engine covers, and it was on the inside and the outside of the face sheet. And the reason it was used, like I said, was not for mechanical properties. It was because of its electromagnetic properties, and also electrical properties, so that it can, with that amount of material, it discharges electrostatic charges. So which was important. And then it was also effective in electromagnetic interference shielding. So, that's part of what, for me, is a lesson learned in the sense that emerging technologies, even though we tend to think of their applications as being decades away, if it can meet a performance requirement and there's no other existing solution, people will use it. Now, there is going to be risk, and so the technology will be evaluated not because of all the what we consider to be novel functions, but really, and those novel functions don't actually factor into the consideration if it's not useful for the required function. It has to perform a specific function that people need. It needs to be ready for insertion on schedule, because the mission will not wait for the technology. And so, what lesson did we get from that is that even though the structural performance objective was not realized, the technology was flown anyway. It was flown because of other performance benefits. So based on understanding of that, I want to talk about how we've evolved in the way we do research in this area, where I view it as a technology pull guided push. And in this case, what do I mean by that? Clearly, we still need to do the fundamental research, but the research that we're doing now is not just for the goal of publishing. The goal is to understand the fundamental science so that we can insert this material as soon as possible into specific NASA missions. And in order to do that, we have to understand what the systems level benefits are. and then try to figure out how we can move from lab to demonstration as quickly as possible. And talking about systems analysis, around 2010, Langley there was an opportunity to work on what we called innovation opportunity teams, and the center was looking at what technology should we be investing in. And nanotubes is one of those technologies that was offered as an option. And when we were given a little bit of money to basically figure out how do we go about in the advancing this technology, it was an opportunity for us to pivot from thinking about adding a small amount of material into a matrix into thinking about how to use the kind of material that had begun to be available then, so that it became a larger fraction of the composite. It was on the order of more than 50% of the composite instead of less than 5%. And the question that we asked was, how much better does this material need to be? How much better does a composite need to be for it to make a difference? So the idea is that if we cannot outperform carbon fiber composites, why would anyone consider using it, right? So this is a systems analysis that was done by Mark McMillan and the Systems Analysis Directorate. And so he was using a model for a launch vehicle, and this is the total mass versus the inert mass fraction. And so we were looking at, figuring out what properties should we be targeting as we set a metric for, what is a measure of success for our work. And so we said, well, let's look at tensile properties and how much better do those need to be. And this model, in this case, he was looking only at the tension-driven components of a launch vehicle. So that's why it's only a fraction of the entire launch vehicle, which is different from the way the initial systems analysis was done, where they just assumed the entire vehicles can be made from carbon nanotubes. And so he said, if this is your baseline, this blue line is the baseline, it's baseline material. And if we are able to get double the specific strength, double the strength of the nanotubes over the baseline material, you can get a maximum savings over here. For this turquoise line is double the strength. So there's a 50% reduction in mass, right? And that 50% reduction is significant when you look at the actual weight, of just the tension-driven components, and it's on the order of 200,000 pounds. And in the context of the entire vehicle, what that came to was about 25% in mass savings. And so that was important for us because it changed the way we viewed how you design, how we measure success and how we plan, how we make decisions on what really works and what doesn't work. So we were aiming for 2 to 3 times improvement in specific mechanical properties so that we can have an overall mass reduction that was meaningful, right? The other thing that we had to, was, I call it the reality check. Structural materials you need a lot of the material to make large components, right? For example, this is a panel made from Petit 5, which is a resin that was invented in the advanced materials and processing branch. And so that was the glue, if you will, that was holding together this carbon fiber composite shown here. And this is a 6 feet by 10 feet. That's the size of this part. And in contrast, we were working with, small quantities of material in the lab, right? So, and the realization is that, I'm going back to this plot, although the nanoscale materials have those properties, when you make it in large quantities like Nanocomp was making, those materials, they're still made of the tiny tubes, which are very strong, but they're not continuous. And so what does that look like? In the sheet that I showed you back in 2012, when we started getting funding again, those properties were really inferior, if you look at aluminum. So you can't use it by itself. When we make composite from it, the best properties we could get were up here, and that's a target, So we knew we could get the stiffness up, but we were only about a third of the because this is a log plot, and so we're only about a third of the specific strength that we needed, and it was a specific strength that was going to give us the mass savings. And so they had another form, Nanocomp had another format that was available. They called it yarn. Essentially, it looked like fiber. And in 2012, the starting point was here. And we were able to actually figure out how to make composite from it so that now the specific strength was much higher. It's closer to the project objective. And here's the other reality check, and it's actually somebody from the team said, well, we set that project objective based on what's called quasi-isotropic carbon fiber composite. So the layers are not all in one direction. But the unidirectional carbon fiber composite has properties which are very similar to the yarn composite that we got. So I always show this, because we work in this technology which is highly hyped, and so we want to make sure that we are not on that bandwagon and we know what the reality is. And the good news with this material, though, is that even though it's not, the yarn is on a small scale, we were able to figure out how to process it to get those properties, but they're not ideal, right? So in the meantime, the other thing that we were doing was, I think of it as rapid prototyping. As a material, typically we would say, wait for the material to get better, to get the best properties, to get performance before you start figuring out how to use it. But what we were doing then was we were funded for a 3-year period, and we had to get from the lab to a flight test. It's just a sounding rocket test, but it was a flight test. And so we were trying to figure out how to learn as quickly as possible. And so we were doing rapid prototyping. And typically, when you use these this carbon fiber, for example, to make articles like this composite overwrap pressure vessel, is being made in a filament winder at commercial scale. But we didn't have enough material. One, we were working with a company to try to push the mechanical property of that reinforcement. And so the material was evolving at the same time that we need to understand how to use it. And so we actually then did a tabletop prototyping equipment. We bought this on a Kickstarter, which was something that didn't exist just maybe, 15 years ago. It was these small companies, startups who were, trying to raise funds to actually get their production up. And we were one of the early investors of what's called an X-winder. What this allowed us to do was to figure out how to wind the material, changing some of the components on, changing the way we think about filament winding relative to commercial scale filament winding. And so one of the things that we had to do was also figure out how to program the winding so that we are winding properly. And that kind of knowledge and the way you think about materials development was something new, for at least for us in advanced materials and processing branch, because typically, when we were doing materials development, is going in the lab, synthesizing materials, scaling it up, transferring the technology to industry, to commercialize it, and then figure out how to use it. In this case, we had to take the material from manufacturing, working with the manufacturer, to actually figuring out how to use it as it's still evolving. And so we did that on a tabletop winder, as opposed to using a pre-pregger, which took up the space of a room in the lab. And what this let us do was use a small amount of material and mimic the process. And so here's where the spool would be set up, and then it went through a dip tank so that we can coat the fiber with resin and then wind it up on a small cylinder. And as we advanced, we knew we had to get to figuring out how to wind the bottle. And so this setup also allowed us to mount the bottle. And so as we optimized the process, we went from winding just a small ring to winding a bottle. And then the bottle had to pass flight safety review, and so it had to be actually manufactured by at Marshall Space Flight Center, where they had a commercial scale winder. And lessons learned from this small winder were transferred to Marshall. One of the things that the team figured out was needing to be able to control the fiber more tightly, as it's moving through and getting coated and wound. And some of the things we tried were interesting because the team said, we need a way to control the movement of the fiber, and they actually used a part of a fishing rod. And that design was actually shared with Marshall, so they were able to modify their commercial winder to be able to control, the winding as you see here. So that's a modification of a large scale machine, and this they had to make about 20 bottles, actually winding 20 bottles to pass the flight safety review. And that bottle went on a sounding racket. Here it's used as a coal gas thruster. So the development went between 2013 and 2015 which was a major part of the Langley effort. And we actually developed computational models to help us understand the composite fabrication. And so we were working across multiple length scales in a very short time to push meeting a launch schedule. It had to be integrated by October of 2016, and that sounding rocket actually flew May 2017. So what are the outcomes of that? What we learned was the systems level guided goal-focused research was very useful for us. Even though it's fundamental research, it helped us understand what paths to take and what paths to abandon. As far as it being used, the project objective being used as a basis for decisions on what the different approaches are that should continue to advance, or that we should just abandon. The other thing is working with industry. Is that the volume of material that we started with, initially they were only available in spool lengths of about 30 meters. And so when we were winding bottles, we were having to tie knots to have this sufficient amount of material to actually wind a bottle, because each of those bottles requires about 600 meters of yarn. And so we pushed the manufacturer to actually advance manufacturing so that they were able to make yarns. When we started, 30 meters was a challenge. At the end of, by around 2015, they were actually able to make spools in hundreds of meters. And so that was part of, because of us telling them that we need that type of we need materials in that format for it to be useful. And we also push them to meet a better consistency in properties so that we can pass the flight safety review. And so the thing that we got from then also was, this is a computed tomography image of carbon fiber composite, which was very optimized. And so you hardly see anything because there are no voids. We were achieving the properties of the CNT yarn composite here, which is very close to this one for carbon fiber composite with this type of material. I mean, you can see that there's a lot of voids in there. And so despite the material not being optimized, it was giving us really good properties that gave us hope that we can outperform carbon fiber composite if we can just optimize the CNT composite. And once we could get mechanical properties, we went back to trying to figure out how can we now take advantage of the other functions. And we were fortunate to have been sponsored for an incubator by the center. And what we did there was to couple two highly hyped technologies, carbon nanotubes and 3D printing. At that time, there was no 3D printer that could handle carbon nanotube yarn. And so we had to build our own printer. This is an example of the advantage of the nanotube yarn over carbon fiber composite. Carbon fiber. You have this strong material that you can have very tight radius on. And so we can make structures like this where we can lay down the material in very tight patterns, which is useful for something like sensors, for example. The other thing is we know that we can print it and still maintain electrical conductivity. So what this is a printed carbon nanotube yarn composite, which was still conductive enough so we can actually hook up a light bulb to a battery through this composite and have enough power, enough current to go through and light a light bulb. So that's one of the multifunctional applications, for example, is that you might be able to get a structural material to also act as a conductor. And we figured out how to get stronger material by laying down the yarn. This is specific stress versus strain for in a plastic. Essentially, this is Altem plastic, and so depending on how we print the yarn, you can have increased mechanical properties. At the same time, this is resistance versus time, and you can see that we can track resistance as we change it, and so it is basically useful as a sensor. People have also used nanotubes now as a heater because this voltage versus current plot shows that you can apply current to increase temperature. So this is the reason people think about multifunctionality. But if we cannot get the mechanical properties up, people who are the users are actually not comfortable embedding a CNT yarn into their structures when it might cause a deterioration in mechanical properties despite these additional functions. So this is just a cool thing for us that we're looking for a multifunctional component that we could print. And so what we did was printed a quadcopter. And you go from a quad design, and the carbon nanotubes were laid in the arms to enhance the mechanical properties. And we also used it as a wire for hooking it up from the battery to the motor. And this is a small quadcopter, but we printed it. It's got carbon nanotube yarn in it. It's the yarn functioned as a mechanical reinforcement as well as a wire, and we were able to fly this vehicle. So it was a cool experience. And so so what we learned from that is that if we're going to transition a technology into the ecosystem, what it really does is displace a state-of-the-art technology, but we have to match performance, or we have to match or actually outperform state-of-the-art. We have to have the material available at scale, meet a schedule, and mitigate risks, and be at an acceptable cost. And we're able to do that in a relatively short period of time instead of waiting decades by making decisions for prioritization based on systems benefits analysis, so that we can have clear and quantified metrics as our goals, so we can measure progress and not wave our hands and say, oh, it's significant benefits. And so when you look at moving from publications to economic payoff, much of our research nationally, tend to be around here in the federal investments tend to be in basic research. But really what we need to move to is user-inspired translational research. And in fact, there is a quadrennial review of the National Nanotechnology Initiative just reported last year, and one of the shortcomings of the initiative was that, I will paraphrase, that the country has not really reaped the benefits of the investments in basic research and commercialization. And so I think as a mission agency, we have a role to play in that space. If I go from the powder to the sheets, and our most recent development was NASA investments, significant investments in manufacturing to move the material from this type to this format so that we can get the high strengths. And we are making progress. The material has evolved in the last couple of years to the point where we are getting properties that in some cases can outperform some carbon fiber composites. So that's exciting. And because we have a common goal, what we're doing now is not just focusing on the technology, but on the ecosystem. We're able to lead by engaging small businesses, which these are the entities that will be the future providers of this technology. We're engaging academia. The Space Technology Mission Directorate sponsored a research institute around structural carbon nanotubes back in 2016, and that's like 11 universities with 22 professors with a couple of industrial partners. And so we're developing the workforce of the future around this technology, and they're all also working together, so it's not stovepipe research. All these university professors are working across the scale toward a common goal, from atomistic scale to macro scale. We're leveraging investments from other government agencies as well, and trying to use public-private partnerships for things like, I'm hoping to get a flight test for this type of material, and moving from research that we do at Langley to transferring to Marshall. And we're able to do that because we have capabilities at the center, spanning materials, structures, components, and systems. And as a government lab, we have the opportunity to provide the pull for universities, users, and suppliers to incentivize this multidisciplinary partnerships so that we can actually have a new material ecosystem. So just, to close out, how has the role of NASA in this landscape evolved? We started in basic research and moved from structural materials and thinking about, starting to think about structural materials, and then kind of got distracted with calling these multifunctional materials. But currently we're involved in technology transition. So we are understanding how to evaluate the payoffs from these investments using systems level benefit analysis, prototyping for structural applications, and acknowledging the realities of technology insertion, that I had talked about. We're integrating new tools as we go along, not just computational materials, but 3D printing and another highly hyped technology, machine learning, as it applies. We're trying to bridge academia and industry, and also realizing, we use publications as a metric of success. I mean, for incentives, but I don't believe they're enough to measure payoff for technology, especially for a mission agency. And so moving forward, we're continuing to understand the challenges of collaborations between academia and industry as we work together for national benefit and coordinating across other funding agencies so that we can develop this ecosystem, not just on our own, and not just sequentially like we normally do, but in parallel to accelerate that. And keeping, in front of us the understanding that insertion is based on performance and on value, and not just on the novelty of a new technology. So again, an important role for us as an agency, as a mission agency, that we have challenging applications that can be used as a pull for technology maturation of such emerging technologies. And we're able to do that because of the capabilities on hand. So I'd like to acknowledge, what I've shown you is really the work of a multidisciplinary team, where we're trying to couple modeling with experiments and also systems benefits analysis. And one of the lessons I learned from the incubator is embedding mission support into our technical team. So I always acknowledge also that we have a very engaged financial analyst who helps us with the business side of doing research at NASA. So that's it. Thank you very much for your attention. And I guess if there's time, I can answer questions.
Yeah, I have one question from Manjula. She says, do you have visibility to work in other countries to comment on our country's relative position in this area's state of the art?
That's a great question, Manjula. So So we are very conscious of what's going on in other countries. We know that this is a technology of great interest. We're very careful, actually, of sharing the advances that we have. This material is now at a stage where it's expert controlled. And so what we know is that where we are is at least, let me just be specific that for the mechanical properties that we're after, I would say that we are ahead of other places because we're working with industry. This is available at large scale. We're the ones pushing, how good this material has to be, and we're working very closely with them. And so we are not doing this in a lab scale. And that is the big difference, I think, commercial availability of this material and being able to prototype components that use it. And we're able to do that because no one else has access to this type of material. So it helps us push the advance.
You mentioned 3D printing related to the yarn. Is the yarn manufactured via 3D printing, or is it laid down with 3D printing?
We take the spool of the yarn and we feed it. It's basically, we use it as part of the feedstock. So what we had to figure out was, 3D printing right now for polymer 3D printing, you lay down the polymer, right? And then when you stop, you can just pull up and move to the next spot. And the challenge is you're putting a fiber down, so now when you stop, you can't just pull up, right? We got to figure out how to cut it. And we actually used the electrical conductivity of the yarn to help us with that cutting. So that was one of the novelties that we came up with, speaking of novelties. We had to figure out how to do that. But yeah, no, the yarn is actually, that's another piece where most people do not have access to that. So they don't 3D print with that. They 3D print with carbon fiber. So it's probably safe to say we're the first to do that, just because of the combination of access to the material and then building the printer ourselves.
A quick one, Mia. So you mentioned about a lot of computational materials work that's going on. Is there enough support, for you to go forward with developing computational tools where you can optimize not only how much fiber volume fraction of nanotubes you need, and where you need to exactly place, to get the kind of properties you need, not only for structural, but also for multifunctional structural applications?
Yeah, so I mentioned that there are 22 professors involved in this. One of those professors is Jamie Guest at Hopkins, and his specialty is topology optimization. And so we're trying to take advantage of that, right? So how can we tailor laying down this material only where you need it? And not yet now, but actually we're thinking about it is, again, those properties, right? Electrical properties and thermal conductivity, how do you use this material in things like for extreme temperature applications? Yeah. So yes, there's been a lot of progress on computational methods that are targeted towards carbon nanotubes because of the Research Institute. Yep.
Yeah, Ed Pryor asking about space elevator.
Okay, Ed Pryor, yeah.
No, Ed Pryor, space elevator, no. Ed, space elevator was one of the dreams, but and I know that there are still organizations working on that, but I think their requirements are far greater than what we're able to do. We're right now aiming to be better than carbon fiber composites, which is already a challenge. I think there's more than just the issue of whether the carbon nanotubes are strong enough for elevators, right? I think people are also thinking about how do those elevators how can you really design them to be useful? So the answer is, it's not one that it's not an application that I really try to not one that we're aiming for. In the current environment, we're happy to get funding to actually feed into a NASA mission. And I'm not sure that space elevator is one of those concepts yet that NASA is really investing in, is it? I don't think so.
And can I ask a question?
Sure.
Hi,
Jake.
Come on here. No, it's a non-technical question. It's about incubators.
Uh-huh.
So you got some funding out of incubator, looks like.
Thanks to you, Ajay.
Yeah, well,
That
that
was
was
you.
just an idea. Thanks to you for putting a nice proposal together. Do you think that thing is still going on, the incubators program?
So after us, there was an autonomous incubator, autonomy incubator,
Right.
and now JF, was trying to collect information, collect proposals, and I don't know that they're gonna have one. They had candidates lined up, but I don't think the center has the funding right now to, at least that's the last I heard, to fund an incubator. But yeah, that was that was a great opportunity for us to not just develop, I think, a technology, but also change the way we think about doing work at the center. Where, like I mentioned, having mission support embedded is one of those things that was important. And in fact, I tried to put a proposal in for an incubator for process development, not just technical, right? I mean, the business process development, and yeah, not getting a lot of traction there. Although, we're still pushing.
With your success with the incubator, you ought to promote this idea to management. It's very beneficial for carrying some high-risk research.
Mm-hmm. Yeah, I think, Clayton is supportive, but the reality of, the way they changed how funding comes to the centers, I think might be affecting that. I think they've centralized a lot of, right, the budget, the business processes.
Okay.
So, yeah, I don't know about the latitude in decision making at the center as far as having the funding to support incubators.
Thank you, Mia.
You're welcome.
I have one more question I think we could squeeze in. Mike Marcolini asked if you knew any more about Mike Smith of Jefferson Labs, who was trying to increase CNT production with a free electron laser.
So Mike, I think they've probably abandoned CNT production with that. What they're doing now is boron nitride nanotube production. And Mike left. I mean, you probably know this, right? That Mike left the center, but he is with BNNT LLC, and they're trying to, commercialize boron nitride nanotubes.
Okay. Well, thank you very much. And that
You're
brings
welcome.
to a close our presentation. Let's give a round of applause to Mia.
Thank you.